So this methodology of light curve plotting and analysis would be a three-part session. Today we'll be looking into the part one. And also, after these three parts, we'll be directly getting into each light curve plotting and analysis examples based on the projects that are completed. Uh, that is on exoplanets, symbiotic binaries, and young outbursting stars. Once after that, we'll be giving some tasks or assignments to you. Based on that, we'll be looking into how you can look into more projects in your future. So this is the course plan as of now. So let's get into it, I guess. All right. So we are moving into an overview. So as we have previously learned in our cosmic journey through various sessions and topics, the study of various compact objects or various celestial bodies like exoplanets and some variable stars all have been going through some very remarkable pace of progress, especially in recent years. Um, Thanks to the continuously developing and advancing sort of observational techniques and data analysis methods that we have. So today we'll be looking into some detailed steps of methodology of light curve plotting and analysis. And we have these five major steps that we put into every light curve plotting and analysis, or any sort of data analysis that goes into our observational techniques. So today we'll be explaining about target selection and observational setup because they consume a lot of time. So today's session is entirely given to these two steps. And in the upcoming sessions, we'll be looking into the other steps as well. First off, let's move to target selection. All right. So for target selection, we need to have some basic criteria, and it is very important to choose our target of the study very wisely. Uh, when it comes to any astronomical observation, the targets are selected based on various factors, like as you can see here, the conditions of the night sky, the coordinates of the point of observation, and the absence of any interference of light, and because these interference of light can cause major light pollution and also cloud up your observation in many ways. Like if you have gone for stargazing events or stargazing, some sort of stargazing shows, you might have observed how well they choose their spot. It could most probably be a hilltop where it is on a higher altitude, and mostly if it is like in the outskirts or some sort of place like that, you might not even be getting your mobile signals there. And also it'll be away from all the light that is ground based, so that could give you a better clarity or better outlook into your celestial objects that you are observing, because these external lights can interfere with your images, can give you some sort of pseudo images sometimes. It can give you some it can cloud up in such a way that it can give you apparent images, uh, in a way to talk, as in like sometimes the light that you receive from a certain compact object could be falling in a straight line, but if you have some sort of environmental lighting or some sort of external lighting that is from your end or from somewhere on the ground, then those lighting can affect it in such a way that the light from the compact object or the light from the celestial body that you're observing could be falling on an apparent position, not exactly at the position it should be falling. So choosing a target that is at the right place at the right time on the right sky is very important due to many factors. All right. So that is one important criteria we need to look here. And also, target selection is also very importantly lying on the schedule. So to plan and schedule the perfect target, either you can do it manually, which in these days in our way, like for example, we are not a primarily working in some sort of observatory, or we are not having a huge access to different equipments to check the night sky all the time and from which part of the world. So if you desperately want to create, or if you want to look out for a particular observation of some sort of event that is happening for a brief time, you can either go manually if you have the right equipments and right resource of data. But what I personally used to use to plan and schedule a perfect target for my observation, I used to refer an online database called Exoworld Spice. So Exoworld Spice will give you some live updates on exoplanetary transits and some star transits, etc. And from this scheduler, you can type up your latitude, your longitude, and if you have a telescope, the telescope aperture, etc. You can add in all the data there, and it'll give you which is the right night and which is the right coordination to give your observation a try. Right. So this database especially gives you updates on some live transits, and this should give you a better opportunity at spotting targets according to your observation. And the figure here will show you the user interface, sorry. So this user interface is just one snap of it. This is the beginning snap of the user interface. This is of the online database called ExoWorld Spice for transit planning and scheduling. So these can be scheduled, and you can either use it to plan your observation. That is one way of utilizing these kind of softwares. And another way of utilizing these kind of softwares is wherein you have a better opportunity at planning your scheduling, as well as planning your observation, as well as scheduling your observation. So let's say you are in a part of the world where you got the right date and time, but you have a very polluted sky. You don't have an opportunity to go to a clearer sky area, although you know this particular event is happening in your night sky from your coordinates, right? But you don't have an opportunity to go to a clearer sky. So what the software will try to capture the images of that day, that night, from that coordinates with a better sky view for you. Okay, so these are some of the benefits of the software, wherein it will capture the images for you. Now, all you have to do is run your data analysis through it, superimpose it, you do all the other manual work, and try to figure a data and analyze it and study about it. So these kind of softwares are also freely available. So through the course, we'll be looking into how to utilize these kind of softwares and how to work on these kind of softwares. We'll be having live sessions on following the software step by step, and also um, yeah. So these are some of the other screens of this interface. So for variable stars, for example, I used another portal called LCO. Right. So LCO observation portal will help you again select the targets and request for target obtention. So yeah. So to one way to put it, ExoWorld Spice would give you more about the planetary data. Right. It'll give you more about celestial bodies that does not emit light of some form. Right. So you can look into various exoplanets, various other planets, various other celestial bodies that may look like planets, and confirm their properties to check if they are planets of some sort or so. Wherein LCO observation portal will give you data about variable stars, and LCO observation portal has an added advantage of doing the capturing the images for you, not only planning but also scheduling. So yeah, so for example, these interfaces that you see here was used by me to prevent some sort of clash of interrupting wavelengths or signals during the transit observation. So I had tried to do the same project uh, on my own manually, because at the time I was working in an observatory and I had the equipments at the time. So as well as I try to do it through the software to see how the differences or how accurate the results can be. So I found a more or less very similar result, but these are comparatively more accurate because obviously the one I did from my from where I was working at the time, those images couldn't be as clear, and I missed out on a few for that particular project. I missed out on a few timelines here and there, so I had to skip while superimposing. So I had to skip small gaps while superimposing, so it gave me a different image which was clearer, but still I think more accurate data was when I put it through the software, at least for that project. So you can get varying results as well. So at the time when I was looking, that was during the winter, and I was looking from the coordinates of Europe. So so there during the winter targets, these were the targets that was available. It gives you a list of the targets that's available from your coordinates. And you can check on how you can take down notes on what kind of observation do you want to conduct. And once you take down your target and you enter all that is required, like for example, I had requested for a data for the duration of this much, and the instrument that they were using was this much, so I can ask them to use so and so instrument. And they look for that particular data, and they plan it and they schedule it, and right at the time of that event happening or that transit happening, you can request them. You can put in a request and it will start absorbing the data from that moment onwards. And once that absorption is completed, they will complete it with some data collection, image consolation, and maybe in another 24 48 to 72 hours you will receive your data. So I received my observation data like this, and I got a data of maybe 1800 files, a zip folder. That is what I received. So then what I have to do is I have to clean the data, I have to remove all the noises, I have to analyze the data, I'll have to filter through it, I have to add filters, I have to um, um, what do you say, superimpose them and try to come up with the analysis that I'm looking for. So this was how my observation looked like through the software. So yeah, so this is about variable stars. So we've discussed about the scheduling of exoplanets as well as variable stars. So that is about our target selection. Now that with the target selection, our major part of our observational technique is sorted, right? Now, next you go to the observational setup, right? In the observational setup, we have, I'm sorry, yeah. In the observational setup, we have 5 different criterias, and these criterias are not always abiding for all the project. Okay, you have mostly around 98% of the time you'll have to follow all of them, but depending also on the kind of object that you're looking into. Like for example, the observatory where I was executing my project, that was called Le Boutier, and that was in the outskirts of Paris in France. So they had an established setup of a TJMS telescope. Okay, so TJMS is what do you say, the initial of one of the famous astronomers that worked or founded that observatory. So it was the TJMS telescope, and this TJMS telescope was used to focus at and observe the target, and this was using a CCD camera to capture the images. So as your telescope or as your equipment has varying features, maybe a lot of these can be automated through that. But on a straight up pile of what you have to do with a manual sort of effort, then you will need to go through each and every step of this in a very precise and concise manner. So we go into each of these now. So first off, about photometric filter. Now, photometric filter are the filters that you add to enhance the various wavelengths that is coming from your images, coming from your source to your telescope. Now, to filter that through, you add a bunch of different kinds of filter to absorb different kinds of wavelengths through the observation, right? So, for example, red filter will help to define the spectrum of light that is being observed. And this red filter will block out all the other wavelengths of visible light. Excuse me. Yeah. It'll block out all the other wavelengths of the visible light that's falling into your telescope. And we must also consider that the observational setup will often contain some extremely sensitive parts, right? Like your telescope structure inside a dome or inside an observatory dome. Wherein, like, you might have visited some observatories wherein your telescope would be set up at a height within a dome, wherein the dome can be adjustable or removed or rotated in such a way where the telescope has to face. Right. So if this has to be done, the telescope has to be contained inside a very sensitive environment. Okay, certain lights, like for example, I'm very much acquainted to the place that I was working in. I'm sorry, I using a lot of examples from there, just to explain. But in that place, we couldn't get inside the telescopic dome even with our flashlights on, mobile flashlights on. Now, this was because our flashlight emits a different kind of light with a different wavelength, which could damage some certain parts of telescope which are extremely sensitive. So you always have inside the dome, you always have a UV filter or a red filter or an infrared filter. Always only those kind of lights will be switched on. We are not allowed to carry any other sources of light. Once or twice wouldn't be a problem probably, but it's like gradual, it'll damage it gradually. So it'll reduce the weakness, it'll reduce the kind of adjustment it has or focal adjustment it has towards the object that you're trying to observe. And yeah, so this could heavily affect the light settings that the telescope may have, and thereby it could adversely impact on the focus and some observational captures of the target that we are looking at. So also, we filter out unwanted wavelengths using different types of filters. As I've already mentioned, we have UV
Yes,
filters, we have
out
infrared, we
in
have green, blue, red. Red is infrared, and green, blue filters, and we have sometimes plain white filters, plain black filters, just to make sure that the light that is falling on
Okay.
the equipment is precisely on point with the wavelengths. Right. So that is about photometric filters. Yeah. Now the camera temperature. So as I had mentioned, I have worked on a CCD camera. We have different types of cameras coming up associated with telescopic views. So CCD camera is nothing but a charge coupled device camera. So charge coupled device cameras will be utilized in astronomy, and they will demand some very stringent temperature control because they are extremely sensitive. Okay, so due to the sensitivity, you can't take this camera out in the daylight. You have to always maintain it in a dark or infrared environment, and these cameras are crucial for some high resolution astronomical imaging, and they're incredibly susceptible to temperature fluctuations in such a way that it can,
for it.
very drastically affect some image quality if it is just slightly oriented left from the actual or the required light settings. Now, also to counteract some thermal noises that we have, which is caused due to some random electron movement, like as I've mentioned, this is charge coupled device. So due to some electron movements, if we have some noises that has occurred, and if we want to counteract those within the camera's components, cameras are first cooled very to a very low temperature, and that low temperature could be at least -30 to -40 degrees Celsius. And once it is cooled down to those extreme down temperature, it is then obtained. So this extreme cooling process will involve some specialized cooling systems, which are integrated into the camera equipment and all that. Okay, so lowering the temperature significantly will reduce a lot of your thermal noises, and it'll give you a somewhat clearer, more detailed astronomical images. And more than getting a clearer astronomical images, the enhanced sensitivity, which is attained through some extreme cooling methods, will allow these cameras to capture even the faintest celestial objects, or some intricate details that we might miss out on a high or highly heated up camera. So even those temperatures on these cameras could make a lot of difference in your observation, is what I'm trying to say here. And even when temperature is being considered, um, not only noises but also warmer conditions in general. If you observe, the observatories are always set up um, in a colder regions of the country, or like in the outskirts, or more into the hilltop sites, like high range sites. So wherein your view on a visible spectrum could be compromised to a limit, but your equipments or the temperature that these equipments are in cannot be compromised at all. Because if your light is compromised a little bit, you can always clean the image or you can remove the noises. But if you're capturing it in that exact same way with equipments that are not in the right temperature or in the right settings, then you have lost your image forever. And probably mostly we would be observing events that would happen once in a while. So we would I remember I had my seniors there who would be waiting for one particular event for 3-4 years straight up. That would be an event that would happen for barely 20 minutes, but they would be waiting for like 3-4 years to just capture that event. So for things that are as important as that, you need to make sure everything is perfect. So yeah, that is it. And the stabilized sort of low temperature environment provided by some extreme cooling techniques will enable a very long exposure times during observation, and that is very important while observing, or that is very important while capturing, where we'll have to get some long exposure shots, and we'll have to get our aperture settings right as well. Now, this stability in the equipments that you use is very pivotal, as I've mentioned, and this is very extreme, especially pivotal in some comprehensive data for scientific analysis for astronomy, and this should mostly ensure some precise and reliable findings. So ultimately, the cooling process plays a very pivotal role in enhancing sensitivity, reducing noise, and maintaining the sort of quality and accuracy for your astronomical imaging and research. So the camera temperature that you use is extremely important here. Moving on, you have binning. So binning is nothing but, okay, is anyone familiar with the term binning in any other forms, in any other than maybe astronomical observation? Anywhere else uh are you familiar with the term binning?
No, ma'am.
Okay, no problem. No problem. All right. So binning is a term that is popularly used. People who are, if any of you are into some direction, short filmmaking, or some sort of, a reel creation or photography or something of that sort, I think binning is a term you would be familiar with. But yeah, okay. So, yeah, when capturing images through a telescope, maintaining a constant magnification, right? The way it magnifies into your target is very important. Okay. And that will imply that some adjustments in other settings like cameras configuration, all of that become very crucial to achieve. And also, we need it at the highest resolution possible. Now, camera binning is sort of a process where you combine pixels, uh, and that is sort of like a pivoting setting, and setting the camera binning to like 1:1 means no pixel combination occurs. So you might be familiar with the term pixels when even your mobile cameras, you would be checking the pixels when you buy to see how good your camera quality is. So when you set the camera binning to 1:1 pixels, that means there is no pixels, that is pixel combination that is occurring there, and this will preserve the individual pixel information as it is. So there is no enhancement there, there is no sort of external enhancing or external lighting that is added, right? So this is the whole point of binning. And this configuration will maximize your image detailing and resolution. Like, for example, all of us at some point must have tried to take a very beautiful picture of the moon, right? Like, we have all tried at some point just with our mobile camera to capture a good picture of the moon. Maybe moon would have looked so pretty outside, but when you click a picture of it on your mobile, it might not have the kind of detail it has. But if your mobile was more a concise device, and if you could put the binning back into 1:1 and no pixels are involved there, then you could be getting a like lot more detail, like how you see it through your naked eye. You could be able to get that, or even more detailing, to be honest. So that is where binning comes into picture. So this configuration will maximize the image detailing and resolution by retaining the original data from each pixel and resulting in some of the finest level of granularity. And this granularity is something that we all face while clicking pictures, right? You see grains like effect when you try to zoom in a lot or so. So this is where binning plays a major role when your magnification is kept constant, and if you're keeping on zooming, the grain thing should not come. That is the whole idea of introducing binning here. Okay. So, like, for example, let's say when you're having a higher binning settings, like for example 2:2 or 4:4. So in this case, there is something called an amalgamate pixels. So amalgamate pixels is nothing but it'll just add on to your pixels for increased sensitivity or quicker image acquisition, and they do all these increased sensitivity or quicker image acquisition, all these at the cost of the image resolution. So sometimes I think even in certain mobiles, like when you click an image, it'll ask you to wait there for some time. It'll show a little round thing with a focus on it, and it'll ask you to just wait there for some time. It'll need time to focus and generate the image, right? So those images are trying to just, they will try to keep it focused for a while, and that has a binning that is lesser than most other mobiles. Okay, that is sometimes very irritating because it takes time. Sometimes you'll just click and move, and then your final image is probably the you know the movement alone. So that is a little irritating, but actually that those kind of images are doing more effort, putting more effort into the image, if you think about it. So your image is delayed, but your resolution could be slightly greater than other images. Right now, if you look into iPhones and all, uh, it's a different story. But yeah, so this is how binning happens. Anyway, so for the utmost detailed and high resolution astronomical images, we always recommend maintaining the camera's binning at 1:1, which is very crucial, and it ensures the preservation of some individual pixel data for comprehensive and precise observation. So that is about binning. And moving on. Now we have a reference star. Now, reference star is also something I've discussed before. And reference star is nothing but you try to keep some other object as your reference to see how far another object is moving, or how far you can get into the details of the other object. So anytime you look, you always keep something reference, so that you don't you can get on the coordinates about it, you can get on various aspects about this particular target based on a reference star which you know a lot more about. Okay, so reference stars or comparison stars will always refer as some sort of reference points, and it will help in mitigating some fluctuations in brightness that is caused by, let's say, by atmospheric disturbances, which are inevitable. Atmospheric disturbances are always bound to happen during astronomical observations. However clear your sky is, or however perfect your light settings is, there will always be some sort of atmospheric disturbances, which will, in some minute way, affect your setting depending on how strong or how perfect your settings are. So that is why we use a lot of different filters. Right. So these reference stars, the purpose of these reference stars is to differentiate some true light variability, and these true light variability that is originating from the observed target, and that is coming up from this target from changes that is induced by the atmospheric interference. And so what we do is, by comparing with the target's brightness with that of the comparison stars, astronomers will be able to discern and isolate some variations unique to the main target. So when you compare and check, okay, my target is giving out so much more light, or so much less light than this, so that sort of comparison is easier to be done, and there is a light fluctuation, or there is a flicker fluctuation. All these can be associated with the reference star that you have. All right. So this process of having a reference star for your comparison will enable a lot more accurate analysis, and will ensure the kind of fluctuations measured are quite intrinsic to the target, rather than you just rely on just your target star, and just your comparative data, and just let it influence by the atmospheric conditions. That will not give you an absolute what do you say an accurate data in a whole. And this will also sort of facilitate some precise investigations that goes after your observation, right? That will help you compare your intensities or brightness or luminosities with the reference or known star that you know. And it'll also help you with some inherent characteristics and behaviors of celestial objects that you can later compare after your observations. And while you do your data analysis, you could compare that too. So that is about reference stars. And you have your reduction frames. Now, reduction frames is one of the most, I would say, most crucial part of setting up your observational system. Now, reduction frames are used to give your telescopic screens or lenses the sort of getting used to part of it. Okay. So if, let's say, okay, one simple example is when we wake up in the morning, right? When we wake up in the morning, and if you, let's say, your bedroom, wherever you're sleeping, has a very bright ventilation, and there is a window that is open wide bright, and you open your eyes in the morning, you will find your eyes immediately trying to, you know uh, it'll take a while to get used to it. Like, you won't be able to open your eyes completely. You will see that all those light is just entering your eyes, and it's just irritating your retina, and you're not able to completely open. You feel like you feel some people feel the sort of sharp pain inside and they're not able to open. It'll take a while for your eyes to get used to the environment. Okay. Ultimately, maybe in another 1.5 minutes, you will be used to it, right? Now, let's say you had opened your eyes into a dark room. Okay. You opened your eyes into a dark room. And once your eyes got used to it and the amount of light that is entering into your pupils were comparatively just growing in, and your eyes are completely open, and then you switch on your lights, you will feel a little more adapted to it. Like you put a smaller light first, and then maybe you'll scroll on your mobile screen for a while, and then you slowly switch on your switch on your light. Your eyes will, by the time your eyes might have readjusted to the light, and you wouldn't feel that irritated, right? So that is the kind of thing that you're doing here. Reduction frames are nothing but you're just making your telescope getting used to what the kind of light that is going to come from your target object, right? So yeah, so reduction frames are used to improve the accuracy and quality of the calibrated data by removing some unwanted noises and signals from the raw images, right? So as the raw images hit your telescope, it shouldn't feel like, oh wait, I'm not able to take this in, it's too much light, or it's too much of a brightness for me. So just to remove that sort of situation, you try to readjust it with a few frames. Like we, for the simplest of it, if I may give you an example, we put a white t-shirt or a white cloth on top of the telescopic screen so that it gets adjusted to a plain white area. Then we put a plain black telescopic screen to just give it, like, to just capture how it is focusing on these colors properly. And then we add different other reduction frames. So once we test through all these colors, and then we try to give the maximum entry of the brightness through the telescopic lens, that's when you are able to find out, okay, how much light is it able to get into this focus, right? So firstly, what we do is a raw image of the target is captured. Then we use a bias frame. Okay, so we have a few different types of frame here. We have a bias frame, we have a dark frame, we have a flat frame. So bias frame is when you try to capture an image with your telescope with a zero exposure. You use a zero exposure to eliminate any sort of electronic noise that it may have. And this is done, the bias frame is done by putting a plain white cloth, or like I say, like a plain white anything. You can just put a plain white t-shirt onto it, or a plain white cloth, and anything that's readily available for you. And we just gather an image just to see how this bias frame works, and it has zero exposure. And then you go for a dark frame, okay, which is used to remove any background static from the picture by using a cover in the same exposure, that is again with a white frame. And then we have a flat frame that is used to remove any optical distortions and any other small flaws in the picture by pointing it at a uniformly illuminated surface. Now, that is after you put a black cloth or a black in anything black, and then you try to, through the black, you try to point it at a uniformly illuminated surface. Now that is how, see, that's how you put a white cloth, zero exposure, then you have a dark frame, again white cloth, just no illuminated surface, then you put a black cloth, try to point it to an illuminated surface. Now that is when the telescope is slowly getting adapted to whatever light it can take in. Now, so each frame type will address some specific flaws. Like, for example, in bias frame, it is to eliminate electronic noise. Dark frame is to remove any background static. And flat frame is to rectify all the optical distortion. So all these are done by specific reduction frames. And it'll address these flaws and enhance the accuracy in astronomical data analysis. Now, that is it with reduction frames. So this is a little something. This was the telescope that I
Yes,
was working on. I just thought I'll just add it as a bit of nostalgia and an inspiration, maybe if anyone wants to try it out.
ঠিক আছে
It's a cool experience. So yeah. So this is the telescopic setup, and this is a
দেখছি
slider door where you can slide. The whole dome can be slid around it, and you can point it to any direction of your event that is taking place. And this is your telescopic setup. And this red light, what you
হুম
see, is the infrared light that is constantly provided in this telescopic setup. All right. So yeah. So TJMS is telescope. Jean-Marc Solomon is the name of the astronomer under whose name uh,
দেখবে তো
this
খাবার দিয়ে গেছে কিনা
observatory was found. And just to give you
দিয়ে
an
যাবে
idea about it, the point of observation was this was the name of the observatory, and the coordinates that I was working on are these. So mostly every time you work on any sort of observation on telescope, the core criteria is that you don't name your place by the name of the place or the country or anything. It's purely based on your coordinates, because coordinate on every point is unique. Okay. For me also, if I take a coordinate right where I'm sitting right now, and if I take it like just 1 meter apart, that's a different coordinate. So it's always based on the coordinates that you're taking noting your location with. Now, the type of telescope was a primary mirror telescope. So, hope you're aware of the kinds of telescope we have. We have primary mirror, secondary mirror, and we have various other kinds of telescope. But most prominent ones are primary and secondary mirror telescope. And this was the basic one, primary mirror telescope. And the setup was a Newtonian Laurent Cassegrain focus attachment. If you all remember, I had discussed about Newtonian and Cassegrain telescopes during our first sessions, but we'll be looking into these once again in detail. And the diameter was 600 mm, and the focal length was 2 meters. So this is just a project detail that I'm giving you all. Now we'll be discussing more about these projects in the upcoming session. So with this, we have come to the end of today's session. Does anyone have any questions, any comments?
No, ma'am.
No questions, no comments? Hmm?
No, ma'am.
All right. So, okay. Uh, that either means you have understood everything from today's session, or probably it just anyway. So it's okay. Our upcoming sessions, you should be able to grasp more, I guess, and we will be looking into each of these steps as well. And yeah, if I'm thinking right, next session we'll be discussing about data acquisition, transit modeling and analysis, and light curve plotting and analysis. We will probably be looking at least two of these three in the upcoming session. And yeah, we'll be discussing the project as well. And I'll be guiding you on how to use Exoval Spice as well as the LCO portal.
madam
All right.
madam
Yes,
to
Brishketa Bera.
to madam website, what do we have to do? That website mention I have.
Yeah, the website, as of now, you don't have to do anything. I've just introduced those websites to you. In the upcoming sessions, we'll have a live hands-on on those websites as well as what to do with those. Okay?
Okay.
Okay. All right. So that is it for today's session. And if you all don't have any more questions, Anuj, are you ready to present?
Yes, ma'am.
Okay. Yes. So I'll stop presenting, and guys, we have Anuj's presentation for today, and it is a new topic that nobody had chosen in our previous presentations. It's EOR, Epoch of Reionization. It's a new topic. So if you all could stay back and maybe just try to see what he is trying to express here, that will be great. All right. So thank you. And Anuj, please start.
Okay, ma'am. Thank you. So, good evening, everyone. Today's topic is the epoch of ionization. So, what is reionization? The Dark Ages. After the Big Bang, the universe cooled enough for protons and electrons to form neutral hydrogen atoms. This era, known as the Cosmic Dark Age, was dark, opaque, filled with this gas, and lacking any light emitting stars or
तीन
galaxies. The
अंदर जाना है क्या
reionization process. Eventually, the first star galaxies emerged emitting powerful ultraviolet radiations. This energy ionized the hydrogen, neutral hydrogen, stripping electrons and creating transparent bubbles that gradually expanded. This process, reionization, transformed the universe from dark to
हमारा
light.
आउट है
Why it matters? Studying reionization is
किसको
crucial
ऑफ
because it reveals how the universe transitioned from its early dark state to the vibrant cosmic filled with stars and galaxies we observe today. So the first pillar is the first stars. So population 3 stars were the universe's first stars, crucial for transforming the early cosmos. Those primordial stars were incredibly massive, 550 to 300 solar masses, and had very short lifespan. They emitted vast quantities of powerful ultraviolet radiations. This UV rays radiation ionized the neutral hydrogen gas, creating ionization bubbles. Population 3 stars were the primary sources driving the cosmic
ट्वेंटी
ionization
टू
process.
कर लो
So the
पे आओ
timeline goes by um, from 380,000 years after the Big Bang. The universe cooled, forming neutral hydrogen atoms and allowing photons to travel freely, ending the opaque plasma state. Nearly 200 million years after the Big Bang, gravity formed the first star, population 3, and galaxies, which began to illuminate the cosmic dark ages. Nearly between 200 to 1000 million years after the Big Bang, intense UV radiations from early stars and quasars reionized the intergalactic mediums, IgM, by stripping electrons from neutral hydrogens. Today, the reionization process is now complete, leaving intergalactic space predominant dominantly ionized and allowing an unobstructed view of distant galaxies. The pillar 2 is black holes. The early black holes played a significant role in shaping the universe reionization.
766
The massive
40
first generation stars, population 3, collapsed after short, intense life, directly forming the first black holes. These black holes grew by accreting surrounding gas, forming superheated disks that emitted powerful X rays. Unlike UV rays, these X rays could travel far, preheating the intergalactic gas from very cold to much warmer temperature. This X-rays make heating made the neutral hydrogen less dense, acting as a crucial secondary source that eased the path for stellar UV radiation to fully reionize the cosmos. The pillar 3 is the early galaxies. The first galaxies played the crucial role in universe reionization. The earlier galaxies formed nearly around 200 million years after the Big Bang, if at redshift between 7 to 10. They underwent intense star formation, generating large quantities of high energy ultraviolet photons. A significant portion of these UV photons successfully escaped the galaxies, known as the UV escape fraction, into the surrounding intergalactic medium. These numerous and active star forming galaxies were the dominant source driving the epoch of reionization, transforming the neutral early universe. The cosmology we generally goes by the CMB optical depth, measuring total scattering of CMB photons by free electrons. Lyman alpha forest
थोड़ा टाइम लगेगा
trace neutral hydrogen distribution to show ionization evolution, and 21 centimeter signals. directly probes neutral hydrogen distribution and temperatures. So these led to few formulas which helps us measure the reionization by measuring the total electron scattering of CMB photons, ratio of free electrons to total hydrogen, measuring neutral hydrogen absorption in quasar spectra, and total ionization photons reduced per unit time. The reionization balance. The universe transition from a neutral to an ionized state was a delicate balance between two opposite forces, cosmic illustrators and recombination losses. In cosmic illustrators, early stars, black holes, and quasars emitted high energy photons, actively ionizing hydrogen atoms across the universe. But in contradiction, the opposite forces were recombination losses, free electrons rejoined protons, forming neutral hydrogens, especially in dense regions, constantly trying to revert the ionized state. So the ionization balance equation
ऑलरेडी दोनों आदमी लाइन से है
led to few formulas
तो
which
उनको भी
explains
बहुत
us the
फर्क
rate
भी है
of ionization from
और
photons
आपको
minus recombination
आउटवर्ड
rate
आउटवर्ड
shows how the ionization
निश्चित है
fraction changes over time
आउटवर्ड से
and
किलोमीटर
temperature dependent rate
आप
at which
किधर
free
जाते
electrons recombine
हैं
with protons.
बगल में जाते हैं एक
Reionization
फर्स्ट छोड़ के
progressed when the rate
बाकी में
of
आप
few
आउट
ionized
डाल सकते हो
outspaced
कहाँ कहाँ है
recombination.
ये वही
This
ये वही
momental
जहाँ जहाँ
process
सील डाला हुआ है
saw the
इधर
universe
जाते हैं
reionization
नहीं जैसे कि
fraction
इधर एक सील
grows
इधर
from
ही आओ उधर आओ
0% to nearly 100% over roughly 800
इधर
million
जाते
years.
हैं
Observational evidence of EOR, Gun Peterson thought, rough, Lyman alpha forest,
तो एक ही
CMB
हो गया क्योंकि
polarization,
अंदर के
early galaxy counts.
परवाह नहीं एक घंटा होता परवाह नहीं
In
टूटी करो मेरा को पता नहीं
In Gunn-Peterson trough, absorption in distinct quasar spectra indicates the presence of neutral hydrogen, showing that the intergalactic medium was largely neutral at higher redshift. Lyman alpha forest, distinct absorption patterns in quasar spectra observed at lower redshift trace the ionized state and clumsy distribution of diffuse neutral hydrogen clouds. CMB polarization, E mode polarization in the cosmic microwave background constrains the optical depth, providing insights into the integrated history and midpoint of ionization. Early galaxy counts, studying the number and properties of high redshift galaxies, estimating their ionization photon output, helping to identify the resources of cosmic reionization. Together, these complementary observations paint a clear and consistent picture. Reionization began nearly around z equals to 10, picked up speed between 7 to 8, and was mostly completed by z equals to 6. Each method offers unique insights into this pivotal cosmic transformation. No single observation fully proves reionization. It's the agreement from multiple independent methods, quasars, CMB, and early galaxies, that confidently maps out our universe reionization timeline. References and key resources: JWST observations. The James Webb Space Telescope, famously known as, provides unprecedented views of earliest galaxies, identifying sources of UV photons responsible for ionization. Planck satellite CMB data, reso- measurement of the cosmic microwave background by the Planck satellites reveals the optical depth of reionization, indicating when and how quickly the process occurred. Quasar absorption studies analyzes the spectra of distant quasars, helps map the ionization state of the intergalactic medium at different cosmic epochs. Theoretical modules and simulations. Sophisticated simulations and theoretical models interpret observational data, helping us understand the complex interplay of
मोबाइल
cosmic
नंबर
structures during reionization.
किसका है आपका
How the four pillars work
बोलो
together: stellar evolution, produced UV photons to ionize hydrogen, compact objects
गाड़ी नंबर
like black holes emitted X rays that heated gas, galaxies, distant UVs, like UV ultraviolet lights across the universe, and cosmology, observation measures and constrains the process. Together, these four pillars op- orchestrated the transformation of universe from dark to luminous. Finally, the key takeaways are transformation of the universe. The epoch ionization dramatically transformed the universe from a natural opaque state to a transparent luminous one, which we all see today. Cosmic timeline. This pivotal event occurred around approximately between 200 to 1000 million years after the Big Bang, market, marking a critical period in cosmic history. Driving forces, it was driven by the combined power of the first stars, supermassive black holes, and early galaxies that formed in the young universe. Future insights, new observations from the James Webb Space Telescope, and upcoming next generation telescopes promise to unlock further secrets of this cosmic dawn. Final, final thought after understanding the whole slides and this topic, we can say that the epoch of reionization represents humanity's quest to understand our cosmic origins, from the first stars to the transparent universe we inhabit. Every photon we detect from Z greater than 6 is a messenger from its transformative era. This is Anuj Maheshwari, and thank you.
Thank you, Anuj. That was a great presentation. I like the way you have compiled the synthesis across. And I have a few questions. Meanwhile, does any of the team members have any questions for Anuj? All right. Okay. Anuj,
Yes, ma'am.
what interested you more about this topic other than the fact that I suggested it? Is
Uh,
there anything interested you?
I went through the recordings, so I was when I was researching, I thought that what all the other members have already completed the most of the topics. They have explained well, so I thought that it will be a great opportunity for me to dive into this new one to
Mhm.
understand this one, and especially uh, after researching, I was surprised that this was the actual start from where the whole luminosity came into place. So I thought
Yeah.
it should be the one to be covered, especially because after that, what the end of the era or the beginning, it all
Hmm.
comes from here. That's why I chose this.
That's a good takeaway you have there, Anuj. And thank you very much for choosing the topic as well, without any hesitation. Thank you.
Yes, ma'am.
So you had mentioned the letter Z,
Yes, ma'am.
throughout your presentation a lot. Can you tell me what Z is?
Z is the redshift we measure. So
Okay.
redshift, as we know, that the expansion and how distinctly the rate at which it is expanding. So the higher the redshift, the more we in past we look to. And since before this, everything was a dark age. So if Z is more than 10, then yes, everything was the Dark Age part, which was nearly lasting more than 380 million or more years.
Got it. All right. And so we often come across when you might have gone through EORs, you might have come across this part where Z approximately equal to 6 is often quoted as the end of reionization.
Yes.
Do you have any comments on that?
What
What is it? Yeah.
So as when the reionization it was complete,
Hmm.
so the time from then till now, everything is in equilibrium.
Hmm.
The energy is trying to be conserved. Every other aspect, considering all the freedom of degrees of freedom every celestial body has. So, um, as from the dark age till z equals to 6 was the
Hmm.
transition period, as even in the slide before,
Yeah,
in
you can
which,
go back to the slide.
yes, even in sorry, uh, sorry. So even in as I said, that even before that, the sorry, what was the topic? I mean, I got missed. Sorry, really
Yeah,
sorry
no,
for that.
my question was Z approximately equal to 6 is called the end of reionization.
Hmm.
Yeah, so what is your thoughts about it? What spectra is it, or mm, what where is it mentioned, or what kind of theorem mentions it?
Um, the theorem I might not be aware of much, but
Like for example here, observational evidence for
yes,
EOR.
yes,
What
yes.
observational evidence constitutes the most for Z equals 6 is being the end of reionization?
Um, all of the observations were together the part of the whole idea of the EOR, to observe the timeline, especially, but the CMB polarization, as we all said, the cosmic microwave backgrounds,
Mm,
which changed and shifted with the higher redshift,
mm,
and the earlier galaxies, the higher redshift galaxies, which aged to way back before everything, or almost anything existed. Those gives us the idea of the whole timeline, um, explaining what exactly happened between 6 to 10, and why 6, after at 6 it achieved the everything got ionized.
mm. Okay. All right. So, one more to add, whatever you have told is right. One more to add here is, hope you're aware about the quasar spectra.
Yes.
Yeah. So the quasar spectra is that, can you tell me what is the level of quasar spectra on the Z scale?
um, I have not mentioned it in slide, but I think
Yeah.
maybe 1100, I think.
On the Z scale, it is less than 6.
Okay. Oh,
Okay. So
okay.
on the Z scale, when it is less than 6, it sort of lacks the complete GP trough, that is Gunn-Peterson trough.
Mhm.
Okay. So when quasar spectra is at Z less than 6, it sort of lacks the complete Peterson trough, and it indicates an ionized IgM.
Okay.
Okay. Now that is the major quotation for the end of reionization. But apart from that, I believe CMB polarization is also a major criteria there. I think you've mentioned it yourself here at the last sentence. Together, these complementary observations paint a clear and mostly complete by Z approximately equal to 6.
Yes.
Yeah. Okay. Yeah, that was one question I wanted to ask. Um, yeah, apart from that, I think among these three, Lie Alpha and Gun Peterson Trough, if you have time, you can check a little more into it. They are very interesting evidences. Okay.
Okay. Okay, ma'am.
All right. All right. That's all. Anuj, my only suggestion for the presentation is um, you didn't have to read everything word to word from the slide.
Yeah, actually, I was thinking the same,
Hmm.
but
Yeah.
because it was a bit detailed and interconnected, so I thought that
Hmm.
each and every smaller parts, like even for example, if going through this slide, I could have gone through the observation evidence of EOR, which are gun penetration trough, Lyman alpha forest, EMB polarization, and early galactic counts. These,
Hmm.
and straight away taking I thought it won't be much effective in understanding the exact terminologies it all considered in individually itself. So I thought that
I
maybe my
understand.
time would be larger, but I had to explain
Yeah,
it all.
no, what I meant is you didn't have to skip any points. What I'm saying is on the slide, next time you have a presentation, just keep this in your mind. When you have a slide, let's say you put Gun Peterson trough, okay, and then you read whatever sentences after that. Absorption in distant quasar spectra indicates the presence of neutral hydrogen, showing that the intergalactic medium was largely neutral at higher redshifts. So you just put one statement there which says one bulletin point that says intergalactic medium was largely neutral at higher redshifts. At redshifts higher than at Z higher than 6. Okay,
Okay,
so you just put intergalactic medium largely neutral at Z greater than 6. You just put that and you leave that as a small point wherein you have your separate notes of
okay,
this detailed sentence.
okay, okay.
Okay.
I got
So
enough.
when you explain, you just explain from your cue cards. And those of
Mhm.
them who wants to look into the slide for clarification can check the shorter points. Okay.
Okay. I,
All right.
I actually didn't thought of that. It was a
Oh,
nice
no problem.
suggestion.
Yes,
I thought
yes.
I
So
the slides must be detailed and everything should be present so that even if after referring, they should be available with every point which I have mentioned. I
makes
thought
sense.
in that
Yes, I
way.
understand your viewpoint here. But when you present, it's always better because you're reading the same thing, right?
Yes, actually.
So some people might lose concentration of what you're reading. Some people might check what's on the PPT, check another slide. So it might get a little confusing. So that's why I told you put shorter points on your slide and you take your notes, or if you have cue cards, or if you look at the point and if you're able to remember the explanation for it, that's well and good. Anyway, just added that, but
Yes,
overall, I like the way you have put your quantitative analysis into it. You've put formula, you've put supporting diagrams, supporting images. Very well.
thank you, ma'am.
So thank you, Anuj. I've graded you. I'll be putting the assessments for your reference soon. Okay.
Sure, ma'am.
All right. Thank you so much. Thank you, everyone. That's the end of our today's session.
Thank you, ma'am.
Thank you. If you don't,
When might will be the next class?
next session should be on Wednesday.
Okay,
Okay. If there are any changes, you can follow the schedule that is being put in the group.
okay,
Latest by Wednesday morning, they'll put a meeting link. If not, then it should be on Thursday or Friday. But the best chances are it's on Wednesday.
okay, ma'am. Sure.
Okay. Yeah. Thank you
Thank
so
you,
much,
ma'am.
everyone. If you don't have any doubts or questions, we can end the session today.
Thank you, ma'am. Good night.
Thank you. Good night.
Thank you, ma'am.
Thank you.
कोई
Bye,
प्रॉब्लम नहीं,
Prashikit
सेम
Beran.
है ना, कम हो तो कोई प्रॉब्लम है, एक्स्ट्रा रहता है कोई प्रॉब्लम। सेम नंबर और 705 डीसी नंबर, 705 का जो नंबर है सेम आएगा मेन और कॉपी में। डीसी देखिए 705 डीसी नंबर कौन सा है? ये नंबर 16153 16153। हाँ, ये ना,